So this week we're going to learn how to determine if data is parametric, and this has a lot of important implications on what type of statistical analyses we can use. So let's talk a little bit about what parametric data is versus non-parametric data. So parametric data has some statistical functions that are a lot more powerful. So in other words, what I'm trying to say is if you have parametric data, then you can and want to use statistics that relate to parametric data because those statistics are much more powerful, they're much more accurate, and they're more meaningful. However, the statistics, the way they work, they require that some assumptions are met. So for parametric data to be true, and therefore for these parametric statistics to be useful, your data has to have a normal distribution, and it has to be interval data. And we just spent some time talking about what interval data is. So what that means is, remember, it's quantitative, it's continuous, and it's rankable. So our example before with lengths would be a good example of interval data because it's continuous. We have continuous lengths, it is quantitative, and you can certainly rank longer lengths versus shorter lengths and so forth. So again, parametric statistics are much more powerful. They should be used if possible, but you cannot use parametric statistics to analyze non-parametric data. If those assumptions of a normal distribution and interval data are not met, then parametric data statistics will give you the wrong answer. So, non-parametric data, this is the case if you A, don't know if the distribution is normal. All right, if the distribution is unknown and you cannot safely assume a normal distribution, or if the data does not meet that interval requirement. So in other words, it's not continuous, rankable, or quantitative. All right? If that's the case, oftentimes you can use a derived variable. So for example, you can turn it into percentage and so forth, and you can take a non-interval data set and use a derived variable to make it interval. But if your data is not normal and it's not interval, you cannot use parametric statistics. So that's why it's really important to determine and be able to determine if your data is parametric or not. Right? So here are the criteria to determine if your data are parametric, and we're going to go over how to test each of these. So the first question you have to ask yourself is the data interval? All right? If so, then you can move on. If that data is interval, does it fit a normal distribution? And here are some parameters that we'll talk a little bit more about, but in order to fit a normal distribution, it has to basically have a bell-shaped curve. All right, so we'll learn how to determine if your data has a bell-shaped curve using Excel. One of the key things here, though, is to remember to create bins, and we'll talk more about that as well. We'll talk about skewness parameter, so we can check this. Again, this is helping make sure that the data is also a normal distribution. And if your data is a normal distribution, by definition, 66.7% of your data should fit within one standard deviation. All right, so remember we talked about our 90% confidence interval. That was with two standard deviations. Does 67% of your data fit with within one standard deviation? Because that's helping us show if it's a normal distribution. And then finally, the mean has to be similar to the median, has to be similar to the mode for a normal distribution. So we'll talk about all of these and learn how to test these together in a bit. So normal distributions basically have that bell-shaped curve that we're used to seeing. And what this means is that the mean, the average, is going to be the same as the median because we have just as many data points that are higher than the average as we have that are lower than the average. So remember, the mean is the average of your data, the median is the middle value of your ranked data. So if you have a perfectly normal distribution, your mean is going to be equal to the median. And while not all data is going to be perfectly bell-shaped, this is really because of sampling error. So as we saw with our heights of people, they created bins, so within 5 foot to 5'1", 5'1" to 5'2", and so forth, you can see that we start to see a relatively decent bell-shaped curve, normal distribution here. Right? And the more data you have, the closer to that smooth bell-shaped curve it's going to get. Now the last part of a normal distribution is that the mode should also be equal to the mean and the median. So in other words, if you have a perfectly bell-shaped curve, your median value, your mean value should also be the highest frequency value. Now, this is a little bit difficult when we talk about continuous data, because remember, continuous data, interval data, is continuous. And so that means, and we talked about this with height, if you measured everyone to the 0.00000 whatever inch level, you would find out that there are no two people on this earth that have the exact same height down to an infinitesimal measurement. So what that means is, by definition, continuous data actually has no mode, because there is no two data points that are exactly alike. So this is why you have to put that data into bins. You have to put that data into ranges that are bins, so that you can classify data together. Right? If we just put these people in terms of increasing height measured down to an infinitesimal scale, we would just have a single line of people, because nobody has the exact same height. You might have two people that are 6 foot and very close to the same height, but one of them is going to be slightly shorter than the next. So we put them into bins, and by putting them into bins, we see this bell-shaped curve. And by putting them into bins, we also get a mode. So this means that the mode has to be defined by our bins. So the mode is defined as the middle value of the range of the bin that had the highest frequency. So for example, here we see that the highest frequency bin is our 5'6" bin. So that means this bin is from 5'6" to 5'7". So the middle value of that range, 5'6" to 5'7", is 5'6.5" inches. And since that is the bin that had the highest frequency, our mode would be 5'6.5" inches. Now that's not exactly right in the middle, but again, this is partly due to sampling error. This is pretty close, and so that's within reason. So if we look at this data, we would say that this has a pretty good bell-shaped curve. The mean and the median and the mode are all relatively similar towards the middle. So that would be a normal distribution in this regard. And so I just want to reiterate one last time the mode. This is something that's going to be highly critical, and this is something that people miss quite often, because Excel will give you a mode, but the mode Excel gives you is not the correct mode. In order to get the mode, you have to have your data into bins, and the mode is the middle value of the range from the bin that had the highest frequency. So distributions that aren't normal distributions, well, exponential distributions. This obviously is not a normal distribution. This type of data cannot be considered parametric, and you would have to use other types of stats. All right, so types of measurements that might have an exponential distribution. Well, for example, bacteria growth. Right? Bacteria doubles. DNA quantity versus PCR cycle. So every cycle in PCR, you're doubling your amount of DNA, so you're going to get exponential growth. Right? Sometimes even synergistic combinations. So if two drugs are synergistic together, then their combined activity is more than the additive activity of each alone, and that's an exponential distribution. Other types of distributions that are not normal, and this is a little bit more commonly what we are working with when we're trying to figure out if data is a normal distribution or not, because there's a lot of data that have kind of a unimodal, meaning there's a single mode, there's a single peak, but it's not evenly distributed. You don't see an even bell-shaped curve on both sides. It's skewed to one side or another. All right? So there are some types of data that can have this type of thing. So for example, here you see most of these values are lower, but we have some values that skew it on out to the higher end. So some examples that I thought of. Dispersal of leaves around a tree. So most of those leaves are going to end up pretty close to the tree, but there are some that are going to get caught by the wind and end up pretty far away. And so you're going to get a non-normal distribution of leaves around the tree. Migration of lions from the lion offspring from parental territory in wild Africa. So, you know, they're going to leave the herd, but they're going to usually leave a certain distance away. But some might migrate quite a ways, and that's going to skew it to one side. Right? Distribution of animals relative to a common watering hole. Most of those animals are going to stay pretty close to that watering hole, but some might move quite a ways. And so you end up with these uneven distributions that would not be considered normal distribution. Right? And so the skewness parameter is going to tell us whether your data is normal or not. So for example, if you have a negative skew, then you have some extra values down here that really don't kind of fit the otherwise normal distribution. If this was a normal distribution, it would kind of go up and would go back down. What this means is that these values are going to basically skew your average, right? And you can see that probably even easier over here. These higher values, there's only a few of them, but these higher values are going to skew your average. And so your average is pulled higher arbitrarily, and your mean is no longer going to be equal to your median, because this is no longer a normal distribution. Don't worry about the actual math behind this, but this math is basically telling you how skewed it is, and you can get a negative skew, and you can get a positive skew. So what do you think the skew of a perfectly normal data would be? If this is measuring how much extra data we have negative, or how skewed, how the data is pulling our values towards the positive end, a perfectly normal distribution would have a skew of exactly 0, because you would even out the things above and the things below would perfectly even out, and you would have no skew. Right? So the higher your skew value is, the higher the absolute value of your skew is, the more skewed your data is, because you can have negative skew and you can have positive skew. Right? And this is kind of what we're talking about here. Here's the problem, because if your data gets too skewed, your mean, your median, and your mode start to get pulled apart. Right? So your mean, your average, is going to be affected by these outlying values more than anything else. So your average gets pulled, in this case, your average gets pulled up because you have a few values that are really high. When you start to include those in the average, your average gets artificially skewed too high. The median gets affected less because these are only a few data points. And remember, the median is the middle ranked value. So yes, there's a few out here. It gets pulled a little bit, but not nearly as much as the mean. And your mode is still over here in that distribution, really close kind of to 1, where one side goes down. So if your data is too skewed, you no longer have a normal distribution, and your mean, median, and mode get pulled apart. And then you can no longer use parametric statistics to analyze this data. All right? So we're going to talk a little bit about how skewed is too skewed. All right, so at this point, I'm going to leave this. I have another video where I'm really walking you through determining the skewness values and how to determine if your data is too skewed. So this is kind of the general overview of this, and I'll leave this here for as a resource. But again, I'm going to move on from here because you can take a look, and I'll walk you through how to test this on another video. So basically, what I'm about to take you through in the rest of this this week's unit is how to figure out if the data is parametric. We already know how to determine if it's interval or not. Now I'm going to show you how to use Excel to determine if your bell-shaped curve, if you have a bell-shaped curve. All right, I'm going to show you how to create bins. I'm going to show you how to create a frequency graph to see if that is near bell-shaped or not. I'm going to show you how to do the skewness parameter, and I'm going to show you how to determine if 67% of your data fit within one standard deviation. And I will show you how to find the mode. Mean and median are pretty easy with Excel, but how to find the mode so that you can determine if the mean, median, and mode are relatively similar within reason. And these are the 5 parameters that your data have to meet in order to be considered parametric. And remember, this is an important thing to test first, because you should use parametric stats if your data is parametric, but you cannot use parametric stats if your data is not. All right? So we're going to try it together. We're going to start with practicing how to determine skewness. So that's the next kind of part of this module. And then I will walk you through all those different parts to determine if the data is parametric. My hints for this is to basically have, from Excel, have your Word document, your Excel file open, and then have the video running, and then pause the video. The video will show you kind of the parameters, and I will walk you through how to do these things on Excel. And if you have your own Excel open at the same time, you can do them as I'm walking through them, and that's a good practice. And then at the end, there is some homework where you can do this on a second set of data to see if you really understand it and if you're able to do it with other data. And you can always go back to my videos to review how to do it if you need it. But this, sorry, this is an old due date. This is not due Monday, March 27th. Do ignore that. Just use the due date on Canvas. But we should be able to work together on this, and then you can finish that homework.